It is my great pleasure to introduce our first keynote speaker, Professor Amnon Shashua. He's Senior Vice President at Intel Corporation, co-founder of Mobileye, and currently the President and CEO of Mobileye. Please join me in thanking Professor Shashua to all his work and the contributions to global community.
Thank you, Radka. Good afternoon. I thought I'll give a lecture about really the challenges that we see in autonomous driving. And if I'll have time, I'll talk a bit about wearables, about OrCam, how we are creating AI as a companion for humans. We start with the visually impaired and blind, but we have kind of a roadmap where every human will have an AI on him. So I'll show some slides if I have time. But most of my focus is going to be on autonomous driving. This is an area that has the potential of changing the world, changing transportation as we know it. And it's based heavily on computer vision, machine learning, artificial intelligence, and in how they all fit together is what I want to communicate in this talk. So before I start, just to clarify something that perhaps many of you or most of you know, but I just want to put it on the table, that when we talk about machine learning or deep networks, AI, that are all synonyms of one another today, there are two forms. One is very, very popular. We all know about it, and this is data-driven machine learning, where basically we have a training set, and we would like to train a learner based on a training set, and that learner should be able to generalize its predictions on new examples. And the idea here is to imitate humans in pattern recognition, imitate humans in natural language processing, in natural language understanding. What humans do very, very well, we would like computers to do, and we're using humans to tag the training set, to tag the data, and then try using deep networks, machine learning algorithms to imitate humans. So this is really the popular form of artificial intelligence today. There is another form, and let's call this data-independent machine learning, where we're not here to imitate humans. We're not using any data at all. And this is where reinforcement learning comes into play. When we have a state of the world, in autonomous driving, a state would be the location of all road users around me and their velocity vectors. Then we have an action. An action, in the case of autonomous driving, would be throttle, steering, brakes, or more high-level semantic decision. I want to change lane, or I want to decide which vehicle I want to take away, which vehicle I want to give way. So it's kind of an action. And then there is a reward, and in reinforcement learning, we would like to optimize the long-term reward, kind of the accumulation of the rewards over a long period of time. And in playing games, the reward is really zero throughout all the actions, and then 1 or -1 or 1 or 0, whether we won the game or lost the game. And what is interesting in this space of reinforcement learning is that if the model is known, that means given a state and action, the probability over the next state is known, the model is known, we can train computers to play against themselves and learn how to play a game. And this is what has been done with the AlphaGo Zero quite recently, where DeepMind trained a reinforcement learning algorithm to play Go at the most advanced levels without imitating any humans. No data of human games was used. So in autonomous driving, we have both forms of AI. We have the human imitation AI, the data-driven AI, where we want to train sensing. We have cameras and lidars and radars sending in raw data into our computer, and we would like to use machine learning in order to understand the world around us. Where are the road users, cars, motorcycles, pedestrians, understand drivable paths, and all the semantic information around the car in order to make decisions. So that is the data-driven learning. And then there is the data-independent learning, which is to make a decision. just like in game playing. It's a multi-agent decision process because our decision affects the motion of other road users. Right? We're not acting in a void space. Unlike sensing, where our sensing results do not affect anyone else, when we're making decisions of driving, our decision affects other road users. Therefore, it's like a game with multiple agents. So those are the two forms. And in autonomous driving, we have both of them. So this is something just to keep in mind. So when we talk about autonomous driving, we have particularly three layers. These three layers are taken from robotics. It's a sense, plan, and an act. With sense, it is all about understanding the world around us, road users, and semantic information about drivable paths from raw data. A plan is that we need to now make decisions. Those decisions could be, what trajectory do I need to take in order to implement my goal? My goal could be, I need to exit the highway in 3 miles from now. Or plan could be tactical and strategic decisions. A strategic decision would be change lane. A tactical decision would be which road users I'm giving way and which road user I'm taking way. And when you're changing lane, you're finding a gap between a vehicle that you gave way and a vehicle that you're taking way. And that could be a tactical decision. And then there is a trajectory planning. Given that you know what you want to do, you want to enter in a certain gap, now you need to path your trajectory. So all of this is around planning. And then acting is control. Once you have the trajectory that you want to pursue, what are the commands to the throttle and the steering commands and braking commands in order to actuate the entire plan. So this is the sense, plan, act building blocks of autonomous driving. So when we look at a solution for this, there are 4 pillars. There are basically 3 plus hardware. So the hardware is we need high-performance silicon in order to run very sophisticated and data-intensive algorithms that receive very, very high bandwidth of data from cameras, and we're talking about multiple cameras, high-resolution cameras, radars, and lidars. I'll not be talking about hardware. Then there are remaining three pillars. One is the visual perception. It's all about the computer vision, the machine learning, the data-driven algorithms of taking the raw data and building an environmental model of what is happening, interpreting the scene. The second pillar, it's called this driving policy. I'll mention what RSS is in a moment, which is all about the planning part. Is given that I know the environmental model, what are the actions that I should take? What are the strategic decisions? What are the tactical decisions? What is the trajectory that I want to take? That's driving policy. And RSS is a code name for responsibility sensitive safety. This is how do we go and guarantee safety when we're making decisions. And in autonomous driving, this is really a crucial area because these machines, because their action affects other road users, they can create accidents or can be involved in accidents. What kind of guarantees can you give to society about the probability of entering into an accident given the decisions that you're about to make? And the third pillar, so these 2 pillars, sensing and decision-making, are obvious, right? You cannot drive without sensing, and you cannot drive without making decisions. The third one, about mapping, is kind of non-intuitive. Why do self-driving cars need a map to begin with? So I'm not talking about navigation maps. I'm talking about a very detailed map of, accuracy of centimeters. Where are the lane marks? What is the information about drivable paths? Where is the merge point between two drivable paths? Whether the boundary is a road edge, whether it's a lane, what type of lane it is, whether it's a sidewalk boundary. So very, very detailed information about the static world around us. And it's not intuitive because humans don't need it. Right? When we go to an unfamiliar geography, like if I go and travel to Rome and I rent a car, I'll maybe use a navigation map in order to know where to go, but I wouldn't need a high-definition map or a detailed map in order to drive. But computers need it because of redundancy. Everything that we do, we have to do it in multiple ways, and redundancy for sensing the drivable paths is only through a map, because the only sensor that can sense drivable paths is the camera, because you need texture. And the redundant sensing for a camera would be the map. And mapping is a serious problem, because how do you go and build these maps to begin with in a scalable manner, and how do you go and update these maps if they need to be true, if they need to reflect reality? You need to find a way to update them continuously. So let's start with the visual perception. So I'm going to go through those three pillars, and let's start with the visual perception. What is our goal with visual perception? The way we look at it is that we need to achieve redundant subsystems. You need to achieve redundant subsystems because of robustness issues, but also because of to do reasonable verification. So reasonable verification is that, say I want to guarantee a certain probability of a misdetection. And that probability should be a very, very low probability. So the amount of data that I'll need to collect would be 1 over that probability. Now, if that probability is very, very low, say 10 to the minus 8, 10 to the minus 9, probability of a misdetection per 1 hour of driving, then the amount of data would be 10 to the power of 8 or 10 to the power of 9 hours of driving, which is completely unreasonable. But if we have 2 independent subsystems, then it's a product of those probabilities. So I'll need, instead of 10 to the power of 8, I'll need 10 to the power of 4 hours of driving for each subsystem. So all of a sudden it becomes reasonable in terms of data collection. So being able to create true redundant systems is critical, not only for robustness, but also for validating the system. And it's also not clear that you can have one sensing system that can reach such low probabilities of a misdetection. But if you have 2 separate, each one acting independently, there is a chance that you can reach the 10 to the minus 4 probability. So what would be those subsystems? So first we say, well, there is a proof of concept that with cameras alone, you can have a full stack, end-to-end driving. And that proof of concept is you and me, right? All what we need is cameras are the eyes and a brain, which is the computer, right? So there is a proof of concept. I'm not saying it's easy. I'm not saying that technology today can do it, but it is achievable because humans can do it, right? So first, we're building a subsystem based only on cameras. And it creates great challenges. It creates great challenges because when you think about, because the tendency of an engineer is to be lazy. What does it mean to be lazy? A camera is the sweet spot of the skill set of a camera is the resolution, texture. Getting 3D information from an image is an indirect thing. It doesn't come directly, like a laser scanner or a radar. So what an engineer would do would say, okay, I'll do the detection from a camera, and then I'll get the range from a LiDAR or a radar. The range is more accurate, it is directly accessible, so I'll do kind of a low-level fusion to begin with. But if you do this low-level fusion to begin with, you don't have the redundancy. It's all going to be one system. So the real challenge is not only to be able to do detections using a camera, but to put objects in 3D at a sufficient accuracy to enable planning and control at very, very high accuracies. This is a big challenge to do with cameras, and others are not trying to cope with this problem. They go directly into working directly with multiple sensor modalities rather than pushing the camera envelope to its limits, basically. Now, what would be the outcome of this? The outcome of this would be 2 things. One, I just said, by building redundant systems, so one system will be camera-based, and then we'll have radars and LiDARs added for redundancy, we really build an autonomous car in the right way. It will be much more robust. But there is another advantage. The other advantage is we look at driving assist. So driving assist today is a very big, lively, and growing business. Almost every new car coming out on the road today has a sophisticated driving assist, and I would say the majority, or I would say basically all of them, this driving assist contains a front-facing camera. In some cases, the front-facing camera is fused with the radar. In most cases, the front-facing camera is a standalone. Right? So driving assist is a very big and growing business, and would like to influence its evolution. And towards the end of the talk, I'll mention that we can influence the evolution of driving assist to really a vision zero kind of a point or horizon where there'll be no accidents at all. So driving assist is volume production. Volume production, every cent counts. So when you think about what can you put in a car, you can put in a car something that maybe will cost hundreds of dollars. You cannot put something in a car that will cost thousands or many thousands of dollars. And the lowest cost sensor that you can imagine is a camera. So if you have a system based on cameras and a computer chip, it will eventually cost hundreds of dollars. If you have a system that you need laser scanners and radars and so forth, it will cost thousands and many, many thousands of dollars. So by pushing the camera processing envelope to its limits, we're not only able to create the proper way of building an autonomous car, but also influencing the evolution of driving assist, because we'll be introducing technologies that can be mass-produced because of cost. So this is why it is very interesting for us to push the limits of camera processing until we reach human perception, to its limits. This is the motivation. Okay, let me show you just a clip of part of the information that the camera extracts. You see here bounding boxes around the vehicles. The red line are the road edges. The green line are the lane marks. The green bounding boxes there were on traffic signs. If there would be a traffic light ahead, you see bounding boxes on pedestrians. Okay, so these are the kinds of information camera processing extracts, and all this is data-driven machine learning, deep networks. You see here traffic signs also being detected. So let's have a look of how this looks like. Here is a camera setting of 12 cameras. These are 3 cameras front-facing in 3 different fields of view, but 150 degrees, 50, and then 28. So it gives us both range and wide field of view. The camera sensors are automotive sensors. It's about 1.3 megapixels compared to what you are all used to as consumers, which are tens of megapixels. And then there are corner cameras and wing cameras, and then a rear camera, and then parking cameras. So altogether, it's 8 plus 4, gives us 12 cameras. And here's a clip that shows you what goes inside. Later, I'll show you a bit more clips. So on the top, you're going to see 3 of those cameras, the front and two corners. And the detections are overlaid. It's going to be a clip, but I'm giving you a preview of what you're going to see. And then the graphics are overlaid on the images. On below left, you see the cabin of the car, that the safety driver is indeed not driving. And then on the right, you see the top view. This is where things are in 3D. So all the detections in 2D are placed in 3D, and they should be good enough to do control. So really the interesting information is the top view. You see pedestrians. These are the yellow bars there. A vehicle is now crossing the junction. The autonomous car is slowing down. Pedestrians would be crossing. Here the pedestrian is crossing. You see it both in the image and the top view. The car is slowing down and continuing and so forth. So all of this is powered just by cameras. So I'll come back to examples later after I complete the full picture of the driving policy and mapping. So let's go for a few slides about mapping. So mapping, building high-definition maps is a great logistical problem. There is a way to simplify this and make it almost zero cost. And the idea is to do crowdsourcing. But how to do crowdsourcing? It's not people with their smartphones sending data. It is the fact that every new car on the road has a front-facing camera. And the front-facing camera is connected to a powerful chip. And the majority of those front-facing cameras on the road are powered by a Mobileye chip. So this puts us in a very good position to add software that could extract meaningful data from the image, send it to the cloud, and in the cloud automatically build maps. So what is this kind of data? It is landmarks. So we're not talking about feature points in every image, because feature points per frame would be a lot of bandwidth. But so we're talking about detecting landmarks in the scene, not landmarks in the image. So landmarks in the scene would be pavement markings, would be traffic signs, would be poles, would be reflectors. Anything that is stationary on the road in the scene is a landmark. So there is a recognition process. So it's not just a feature point. It is an area in the image that we know what it is so that we can later match it. So these are landmarks, and then collect the lane information and put it all together, the lanes and the landmarks, and it's about 10 kilobytes per kilometer. So just to give you an idea of what is 10 kilobytes per kilometer, say a car drives 20,000 kilometers per year, it's about 200 megabytes of data. 200 megabytes of data, sending it to the cloud is about $1. So it's a cost of $1 per car per year. So this, when I say it's almost zero cost, this is what I mean. So now this data goes to the cloud, and in the cloud it's pieced together, and a high-definition map is being built. So here's a clip that would show you just what this is. So the clip, on the left-hand side, you're going to see the map data projected onto the image. So the vehicle localizes itself into that map by detecting landmarks. The landmarks are the yellow rectangles that you're going to see in the clip. And the lines are map data that are projected onto the image space. Now, to get a sense of accuracy, if the line sits exactly on the lane mark in the scene, it means that our accuracy is at level of few centimeters. Because if there was a misaccuracy, you would see the map data, the lines not aligned with the true lane marks in the scene. On the right-hand side is the same thing, but projected onto Google Earth, so you can get a sense of, so you can see those lines, which are the map data, they sit exactly on real information in the scene, so the accuracy here is really few centimeters. And you can see the density of landmarks, so it's not per image, it is per scene. So this is why the bandwidth becomes very, very small. So what have we doing with it? First of all, we mapped all of Japan. So we have vehicles already starting to send data from BMW fleets, a few weeks from VW fleets. We have our own Mobileye aftermarket unit. About 20,000 of them are now on the road sending data. So all of Japan highways, 25,000 kilometers, have been mapped, and it's completely automatic. The data arrive, and then a press of a button, the map is being created. Just here some statistics about the kind of data, the number of signs, the number of poles, the number of lane marks, road boundaries, and so forth. All this data for creating the map, and it's all automatic and within hours. That's it. Here's data coming from BMW production vehicles. This is data from Munich. So all this data is there to start building maps automatically. Then you can start getting insights, because you can think of a camera as an intelligent agent, right? There's someone there in the car watching the scene and making notes, right? Sending landmarks, sending lanes, but it could be more than that. It could be, here I see pedestrians. Here I see, a bus stop, and so forth. So, and then I'll show you where's the need for getting more and more detailed information about the scene. It's not only for building maps. So, for example, from here we see that 2 bus stations, and most of the pedestrians are on one side of the bus station and not on the other side. So this information can be very, very useful for helping cities in terms of smart cities planning. Here is information about construction areas. So the camera detects a construction area. These are the green, the yellow circles near the arrow. And also there's information about the average speed over time. The average speed went down from 60 to 45 kilometers per hour. So put this together, you know that there is now a construction area there. And again, all of this is automatic. So you can start generating insights from this. Here is area being mapped in Israel, in Munich, in New York, and so forth, all over the world. This is another use of a need to really extract a lot of meaningful data from the image. So this is a cooperation with the UK mapping agency. It's called Ordnance Survey. And here the application is for utility companies. So the idea is to align underground information like water pipes, gas lines, and above the ground information like manholes and traffic signs in order to get a complete alignment. So when you go and drill a hole someplace on the road, you know exactly what you're doing, and then you're not going to hit a gas line or water pipe. Today, this process of getting an approval to drill a hole someplace takes a long time. Could take weeks even until you prove that actually you know what you are doing. So now all of this can be done automatically. So this is a clip by Ordnance Survey with the kinds of information that are being detected automatically by utility vehicles, about thousands of vehicles driving in the UK, collecting and sending this data for maps. Here is just a small list of what the camera is detecting, right? Overhead foliage, power distribution pole, overhead cable. As I said, imagine the camera as an intelligent agent and what it can give us. Okay, so now that was mapping. Let's go into driving policy. But when we talk about driving policy, it's all about the decision making. We really have to talk about safety. And safety sounds like a very boring issue. So first of all, it's something that everyone says safety is the most important thing, but nobody really defines what they mean about safety. And really the challenging part here, you can be safe by not driving. So if you want to be perfectly safe, you simply don't drive. Or you can drive very, very conservatively, very, very slowly. And then you claim that you are safe. But if you drive like that, you'll block traffic. And if you block traffic, no city would want your autonomous cars to drive in the city. So the real challenge is how do you balance agility to drive like a human with safety guarantees? And they contradict each other. Say, for example, I want to define what cautiousness is. And I can come up with a very legitimate definition of cautious that a lawyer would love, but it's completely useless. So let's define. Let's assume that when I want to change lane, let's define cautiousness such that my motion should not affect anyone else's motion. So when I change lane, all other road users, all other cars will continue with their same speed. I'm not affecting them. So this sounds like a very, very cautious maneuver. Right? My motion does not affect anyone else. Therefore, there's no reason that an accident will be created. But we can all agree that this is useless. In most places in the world, you'll never be able to change lane. If you change lane, somebody needs to slow down. So we need to find definitions of what does it mean to have a cautious driving that will enable agility, that will make sense. And this is where things become ill-defined, because if somebody needs to slow down and that someone did not slow down and hit me, then what do I do? What do we do now? Who's to blame? Okay, so this is why it's a conundrum that no one tried to really tackle directly. So what we did, we published a paper which really formalizes everything. So, but before I tell you about this paper, let's look about real driving in the world. This is from Israel. So Israel is, assertive driving. So we'll see, for example, this car with a circle. It will try to change lane to the left, to merge to the left, and we're going to fast forward this clip. And you see, this poor guy is not going to be able to complete the maneuver. Right? So now, driving in Israel is not unique. It's a similar culture like Rome, like France, and this guy with the long truck, it's going to be minutes. So we're fast forwarding. Right? So this is how real driving looks like. Right? It's not that you are driving in a vacant parking lot and you're changing lane and everybody lets you to change lane. Right? So we have to tackle these kinds of situations, and then what happens if somebody hits me? So. Right. How do we handle this? And we see that this is an issue, right? I redacted the name of the company because that's not the point. The point, it happens to everyone, that autonomous cars that are being tested today are driving so conservatively that are annoying other human drivers. Right? And the question is why is this happening? Well, so when we looked at it, we said, well, this is happening because if there isn't a formal definition of what dangerous is, then I must be conservative. Because if there was a definition what dangerous is, I would reach until that threshold of what dangerous is. I'll not pass that threshold, but that will give me the agility. But when I don't know what is the definition, I don't know what is the threshold, then to be safe, I simply drive too conservatively. This is why a definition of danger needs to be done formally. And then there is also technical issues about driving policy. I'll mention it in a moment. So this is the paper we published slightly more than a year ago. With the idea is that we need to make this public and not keep it as proprietary, because in order for this to work, we need to create a coalition of industry players, of suppliers, of car manufacturers, and eventually regulatory bodies to standardize what we want to do here. So it has to be open, and we had great success in the past year. But first, to tell you what we're doing here. It's a formal model that defines what dangerous is and defines what a proper response, once you're in a dangerous situation, what a proper response it would be. So now you may ask yourself, okay, what's the big deal? So these guys are philosophizing about, what does it mean to be cautious? They have a bunch of lawyers sitting there and defining definitions. It's a bit more tricky than that. It's a bit more tricky than that because you need to optimize 3 axes. 2 of them are kind of obvious. The third one is very, very not obvious. The first one is soundness. If I want to define danger, I need to define what cautiousness means. So I need a definition that complies with the common sense of human judgment of what cautious is. Second, it needs to be useful. All what I said before about usefulness, I need to allow for agility. I can't just maximize the soundness axis and ignoring the usefulness axis. I need to be also useful. So these are 2 axes that I need to optimize. The third one, this is where it becomes non-intuitive. The third one, we call this efficiently verifiable, and this is where the mathematics come in. I need to prove that my interpretation of danger and cautiousness is implementable in a machine. It means I need to conform to the inductive principle. It means that when I make a decision, I need to be able to tell immediately whether this decision is safe or not safe, rather than rolling out the future and looking whether in the future my action will create an accident or not. So it means I need to be immune to butterfly effects. So I need a model that is inductive. So it not only is sound and useful, but it's inductive. And those 3 axes needs to be optimized simultaneously. Okay, now, and this is what we did. If you want more information, you can go and read the paper. We are creating a coalition of industry players. Recently at the CES, we announced that suppliers like Valeo, big automotive supplier, has joined. The China ITS has created a standard body around standardizing RSS. Baidu has put RSS into their open platform, and the coalition is being built because it's really a model that makes a lot of sense. Another point about okay, I'll skip these slides. It's not that critical. So let me show you some examples. So now, in each example I'm going to show, you're going to see a top view from a drone taking a picture, taking a clip of the maneuver that you're going to see, and then you're going to see from under the hood, from inside the car, just like the clip that I've shown you before, what is happening. So what you see here is a car blocking traffic, and the other vehicles, other road users are finding their way out of the lane, and you can see this blue car with the Mobileye Intel logo on top. That's the autonomous car, and you'll see that it's maneuvering, just like a human. It's not letting anyone else, take advantage of it. Right? So it's moving nicely, right? And this is under the hood. Well, I'll run this twice. First, have a look at it, and then I'll explain what are the color codes here. So let's run this part again. So what are the color codes? When the autonomous car makes a decision, let's assume a decision to change lane, then it needs to make a tactical decision of which vehicle to give way and which vehicle to take way. So a vehicle that is given way is coded in red. a vehicle that you take away is coded in green, and when you want to change lane, it's a gap between red and green. Okay? And this decision is changing all the time, because let's assume that you decided that you want to take away from a certain vehicle, but that vehicle is not allowing you to take away, right? So you don't want to create an accident. So then you relent. So you'll see that this decision is changing again and again and again. So green turns into red, and now it changed lane. Let's look at the next one. Here's another interesting one. On a artery road, a pedestrian is going to come out of a car. You're going to see it here someplace at some point. I'll point to it. When it happens here, the pedestrian is coming out. You see it also here. And now the car is maneuvering out. You can see it's fighting its way with the steering wheel here, and in very dense traffic, and getting out of it. More urban scenarios. A car coming out, slowing down, and then later in the junction, the autonomous car is going to give way to the cars coming from the right, and it does it in a very smooth manner. I'll skip this. Let's see another one here. There's going to be a blockage. Blockages is tricky because you need to distinguish between a blockage and a traffic jam. Blockage, you want to kind of overtake. Traffic jam, you need to wait. And it did so quite very agile and very quickly determined that it needs to overtake. And you can see this from under the hood, inside the car, the detections and the decision making of what is going on here. Last one here is the junction. Cars are coming from the left. They should give way to the autonomous car. But if you're not assertive, nobody will give you way. So let's look at the vehicle coming in now, right? It took its, right? And the same thing, you can see it from under the hood from here. Okay, let's give it a bit more. So you can see red meaning it's giving way, and green, it's taking way. Okay, so to end this part, kind of the more global strategy behind all of this. Right. So we have driving assist and we have autonomous driving, and there are cross links. One cross link is kind of obvious. The second one is less obvious. The obvious cross link is the one on the top. All what we do in driving assist are tested over millions and millions and millions of miles. So components are being tested, are battle tested to very high levels of degrees. Therefore, those components can go into autonomous cars. You know that they are already been tested. Say pedestrian detection, say vehicle detection. They are tested over billions of miles now. Okay? So this is one cross link. The other cross link is a bit non-obvious. When we go and build the technology for autonomous cars, we think, what technologies can we migrate into today's domain, into today's driving assist? And the fact that we are developing the technologies around cameras and then later adding radars and lidars around cameras gives us a very good position in that migration, because cameras, as I said, is low cost and can sit on production vehicles. So there are two areas. One area is about the mapping. Every car having a camera sending data to the cloud, this map data is sent back to vehicles and can enable driving assist at much higher performance levels. So for example, you can support ACC or lane keeping assist even in urban roads or when the road marks are not clearly painted, because you have map data to allow you much better driving assist. So mapping technology, which was developed for autonomous driving, can and is affecting the evolution of driving assist today. But there's another point, and that other point is when you think about the revolutions that are going on here, there are two revolutions, and people tend to put those two revolutions in one bucket. And the point that I'm making, they are actually spread into two buckets. One revolution is the revolution of transportation. If you have autonomous cars, the way transportation is going to unfold is going to be very different from today. The way we own cars, the way that cities plan their parking lots and so forth, the way mobility on demand is going to look like. It's all going to be disrupted and changed. So this is a revolution of transportation. But there is another revolution, and that revolution is saving lives. And people tend to put them in the same bucket. So if all cars would be autonomous, clearly nobody would get killed. But that is when pigs will fly. That will take time. You can do the revolution of saving lives using controlling the evolution of driving assist to in a proper manner. You can actually, just through driving assist, create a true vision zero where there will be no accidents. And this is something that we have been doing, taking this RSS, which defines safety for robotic cars. And recently we published another paper showing how this can be used for autonomous driving, for driving assist, and creating a formal model that you can prove that if all cars are equipped with this kind of new driving assist, the likelihood of an accident will be negligible. Okay, so let's, in the remaining, say, 7 minutes, I'll go into AI for wearable. So in what I described so far, the artificial intelligence was in the car. So we were sitting in the car, and we were surrounded by artificial intelligence. Artificial intelligence are sensors and computing that understands the world around us, protects us from getting into an accident. This is a driving assist, and eventually will drive the car for us. And the kinds of AI that is needed there encompasses all the forms of AI that we know, both data-driven and data independent. This is the driving policy. But now let's take another step and put the artificial intelligence on us humans, right? And think of AI as a companion, right? We have another sensor, another eye, and another brain always with us, monitoring the world around us and providing us value, somehow providing us value. And this is what OrCam is about. And we did this in phases. Phase one is, we ask ourselves, let's identify a segment of population in which having AI as a companion is an enabler, is critical, right? For me, it's not critical. For you guys, it's not critical, right? You can handle the world without any AI, right? But with someone who is visually impaired or blind, it is critical. It is like having a helper standing beside the person, seeing the visual world, understanding the visual world, and whispering into the ear of the user what he's supposed to see. There's a pedestrian here, that's the name, this is Joe, and here is a newspaper, and these are the articles of the newspaper. If you point your finger on an area, it will read it to you. This is a product, this is what the product is, and so forth and so forth, just like a human standing beside you and giving you information. So before I run this clip, so we built this device. There are about 100,000 blind and visually impaired today using this device. So just devices, this what you see here. So it's very, very small. It clicks onto eyeglasses, and there is a camera on front, and it continuously scans the visual world, and it does a number of things. First, it identifies people. So if someone familiar is in front of you, it will say the name. It reads text, all possible text, on newspaper, books, text in the wild. It recognizes hand gestures. So if you're pointing on something, or you're doing stop, or you're raising your hand, it will tell you at the time. So it has a family of hand gestures that it will recognize products, recognize money notes. It can understand, has natural language processing. You can speak to the device. It will understand and provide you information, and gradually adding more and more computer vision and natural language understanding capabilities to make this a real helper beside you. So let me show you just the beginning of this. Okay, we need the sound. Let's do this again.
Oh,
That's what the device does?
yeah, sure. Oh, it already recognized you. Let's see who else. Oh, hi, Gil.
So just if you haven't noticed it, the moment you see someone familiar in the visual world, let's say it says his name. And it said the name of the person twice. Jonathan Wexler was in front of her, and then she turned her head. There was another guy, this guy here, and it said its name. So the sound here is not very good.
Hi.
What else can you do?
So the device can read from any printed surface and recognize colors. Let me show you how it works. Take newspaper and read by pointing.
That's the hand gesture, right?
The most coveted free agent slugger on the market has final.
And it starts reading the newspaper. I'll skip this,
Open my
and this
hand
is a stop
and it just
gesture.
stops.
And it then will recognize products and many other things. So what I want to show is under the hood, right? Because it's not a marketing lecture. Sorry for that, right? So a bit under the hood. So while a person is moving, you're going to see overlays on the video. So for example, here it says a door. I don't know if you can see it from here. See here it also says a door. Let it run. And this is being done at frame rate. So openings, doors, it will say staircases, people. Let continue a bit more. Business card, screen, it knows they're looking at the screen. Okay, here's index. Now it does a parsing of the text, stop sign. Let's continue a bit more. Here's another monitor, computer monitor, so it knows to distinguish between them. Here is money notes. So it has a memory of about 500 different types of money notes of over 23 countries. All right, so a bit more. And everything here is done in frame rate. And then well, let it run a bit more before I skip. Okay. Okay, that was a raising hand maneuver. People, stairs. It's written there, stairs on the blue. All right, so it knows about stairs. Now you can imagine why this information is important. Say imagine that you are blind. It's difficult to imagine, but no, imagine that you are blind, and at some point you're misoriented. If you know if somebody tells you where the stairs are, tells you where an opening, where a door is, that's very, very powerful. But you can think of doing more. Let's assume that you don't want also only to detect text, but also logos. McDonald's. It's logos around there. And why would this be very, very powerful? Because again, assume that you are blind and you are in your favorite mall. Now, if somebody would have told you on your left is McDonald's and on your right is Starbucks, you know where you are. But let's assume that you are misoriented. Now you don't know where you are. Right? So now the glasses will tell you, oh, this is McDonald's, this is Starbucks, and so forth. So being able also to recognize logos is very, 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 very powerful. So for example, here's Adidas and so forth. So this is also going under the hood. So all what I showed you before, plus this, is continuously going under the hood. Also, where do we need natural language processing? Say, for example, you're looking at a menu. Now, looking at a menu, you don't want the computer to simply read you all the text. It will take forever. You'd like the computer to understand that this is a menu, to parse it, and then do a Q&A with you, right? It knows that this is the main course, these are the appetizers, if you want fish or meat, and so forth and so forth. So kind of have a discussion with the computer until you find what you need. So this is also being done by the device. We also took this technology one step further. We recently launched a Kickstarter which ended 2 days ago. So it's too late for you guys. This Kickstarter is taking a device, and you see the size of the device here, which has the capability, subset of the capabilities that you see here. So it clicks onto your clothes. It will recognize faces instantaneously all the time, match it to a database that you have, and then you can build this database on the fly, and also recognize text, business cards, and name tags. So it can create an experience of someone from your past. You see him, you'll know immediately who this person is, because the name will be sent to your smartwatch or to your earphone or to your smartphone. But also keep track of all the meetings that you have done. And then in the future, we're also going to put natural language understanding onto it. So while we're having a discussion, key topics can be extracted, or if I'm saying something actionable, let's meet next. Let's plan to have lunch next week. This is something actionable will also be extracted and put into my notes on my smartphone. So you can start thinking of AI as a companion gradually. So this is going to be delivered to 900 people in March, so in 2 months from now, as it's kind of a big experiment that we're doing. Last thing, you can think of now combining vision and sound together. There are several research papers around that area in the past a year or so, and around what's called source separation. So source separation is what's also called the cocktail party problem. Again, I'm finishing in a minute. Cocktail party problem, where if many people are talking simultaneously, we humans can isolate the voice that we want to focus on. If you have hearing disability and you have hearing aids, the hearing aids are not that sophisticated and they'll amplify the voices of everyone. Right? But now if you have a camera watching a person, you can take the video and the sound together and isolate it's almost science fiction, isolate the voice out of it. So let me show you a simple experiment just to give you an idea. So I'll be reading text, and while I'm reading text, other people are going to read text around me at the same time. Sound
again. Fit the perceptual silence of each component within the estimated source. For instance, low frequency
cacophony of voices. Now you can see here on the left-hand side is the zoom on my lips. So now
these energy ratios do not always fit the perceptual silence of each component.
So it's really a very clean separation.
For instance,
so
low frequency components.
This could be a significant add-on to hearing aids. Okay, so we can take this technology of computer vision and natural language processing, put them together, and create also products that will aid people with hearing disabilities at a much higher level of what technology can do for them today. Okay, I'll end here. I think do we have time for a number of questions? Yeah, okay, so be happy to take questions.